It turns out that with many of the distributions that we work with, for example, the exponential, the normal, the Poisson, the binomial, we can pretty easily get a complete and sufficient statistic. And so the next two slides, and this video in general, is meant to define the exponential family and show that, well, at least we'll claim that the distributions, many of the distributions we work with are part of the exponential family, and therefore there's an easy way to get a sufficient and complete statistic, and thus an easy way to get the uniformly minimum variance unbiased estimator. So let's first define the exponential family. So if we have a random sample x1 through xn, it's said to be from a one-parameter exponential family if the joint PDF of the sample can be written in the following way. So joint PDF, parameter theta. Basically, we can split up the distribution into some functions. The first function being just a function of x's. A second function being a function of just the parameter. And then a third and fourth function sitting inside of an exponential. So e raised to some third function that's just a function of the parameter, and a fourth function that's just a function of the data. Now this might seem somewhat arbitrary and maybe complicated. Let's look at just a quick example. If we had our x1 through xn IID exponential with rate parameter lambda. And notice the actual exponential distribution that we've worked with is different from the exponential family of distributions. The exponential family means you can take the PDF and factor it in this way. The exponential distribution is just the distribution that we've worked with the PDF that you're familiar with. So in this case, the joint PDF will be the product of the marginal PDFs. So we should have a lambda raised to the n times e to the negative lambda times the sum of the xi's. And the exponential distribution is easy in a sense to show that it's from the exponential family, because, well, our d of x is here, our c of, in this case, lambda, the parameter, is here, our b of lambda is here, and our a of x is just the constant function 1. So the exponential distribution is already sort of split up in a nice way to see that it comes from the exponential family. It turns out, though, that the binomial NP, where p is the unknown parameter, n is assumed to be known, the normal distribution with mu 1, or mu where sigma is known, the Poisson distribution with rate parameter lambda are all in the exponential family. And so we've just shown it for the exponential distribution. I'll leave it as an exercise for you to try to show it for some of these distributions, and maybe I'll give you one of these as a homework problem. So the reason why the exponential family of distributions is important in this context is because it helps us find a complete and sufficient statistic for the distribution. So if you go back basically what this theorem claims is that if you have a sample from a one-parameter exponential family, then d of x is a complete and sufficient statistic, and based on that, you'll easily be able to find the uniformly minimum variance unbiased estimator, because if you have a sufficient and complete statistic for the distribution, you can find the function of d of x that's unbiased, and you have the best unbiased estimator, meaning uniformly minimum variance. So notice where the d of x shows up, right? It's e raised to some function of the parameter times a function of the data. Well, for the exponential distribution, we see that the sum of the xi's is sufficient and complete based on the theorem, right? Because this is our d of x. So what about for the Poisson distribution? Let's look at that example that we've sort of continued through a lot of our development of these concepts. So if we let x1 through xn be IID Poisson with rate parameter lambda, well, let's write down our joint distribution. So f of x lambda is equal to e to the minus n times lambda raised to the negative sum of the xi's over, well, we'll have a product from I equals 1 up to n of each xi factorial, and then we'll have a product of indicator functions telling us that x must be either 0, 1, 2, etc., right? Potentially unbounded. Well, if we use our exponential and our log as inverses of each other and sort of rearrange this distribution, we can show pretty easily that it's among the exponential family of distributions. So we'll keep the e to the negative n lambda out front, and we'll include the product of the indicators divided by the product of xi factorial. And then we'll work with this term here, the lambda raised to the negative sum of the xi's. And what we'll do is we will exponentiate and then take the log. So exponentiate and take the log of lambda to the negative sum of the xi's. Well, we can use law of logs actually to break this apart, and so we'll have that whole first term e to the negative n lambda times the product of the indicators over our product of xi factorial, and then we'll have e raised to the negative log of lambda times the sum of the xi's. And at this point, I think we've written this in the form of the exponential family of distributions, where our product of indicators over our product of factorials, we could call this our a of x. This is just some function of the sample. And then this term here, we could call our b of lambda, it's just a function of lambda, so a function of the parameter. And then c of lambda would be this negative log of lambda. And then our d of x is the sum of the sample. So what we've done so far is just written the Poisson distribution and shown that it comes from the exponential family. We've factored it in just the way that, that we get in the definition of the exponential family. But if we're using the theorem here, the theorem says that if we have something from the exponential family, then our d of x is complete and sufficient. Well, look what happens here. We get as our d of x the sum of the xi's. So we've been building things up all along, not knowing about the exponential family of distributions, but working with the Poisson distribution that is in the exponential family. And we had to find, maybe the hard way, showing that the sum of the xi's is sufficient and complete. But what this here shows, right, using this theorem, we get it for free. We know that if we can split up the joint distribution and show that it's from the exponential family, then we just read off the d of x as sufficient and complete.